So the way in which we classify using logistic regression is by creating a straight line as a decision boundary, right? But when we speak about k-neighbor classifier, we see the data points that it is closer to, and based upon that, we associate that the new data point to a given class.
Right.
So the algorithm or the logic in which we are associating a given value to a class is changing between logistic regression and k-neighbors.
Yeah.
Similarly, whenever we are speaking about any new other data point, like new algorithm, like for example, decision trees, they use a completely different technique or a logic to differentiate various classes.
Okay.
Clear?
Yep.
So let us see what is a decision tree classifier and how does it classify various data points, etc. And so on. So let me share my screen and have D3. Yes, here you go. So let us see that this is our data. Okay. To make it more better. Here you go. I hope you are able to see it better now, right?
Yeah.
So this is our data. So on a given day, what is the outlook, temperature, humidity, wind, and decision to play? This is our data. Can you tell me what is the X and Y in this data set?
Y is the decision to play.
Okay.
And X can be any of those.
Generally, all or these are X's. Okay.
Yeah.
Except the day.
Correct.
Day is just a serial number. Right. So output, temperature, humidity, and wind, all of them contribute to the final output, decision to play.
Right.
So these are our X and this is our Y.
Right.
Okay. So decision trees work on a very common principle. Okay. Imagine that you want to go to a vacation. So when you want to go to a vacation, imagine imagine I'm a tourist and you are the head of a travel agency.
Okay.
So I come and I'll tell you, sir, I want to go to a vacation. So can you suggest me some places? So what do you say? What will be your natural reaction?
So we'll ask him some questions like his preference, his budget.
Very good. So exactly, very good. So first, you directly do not say, okay, go to Kulu Manali, go to Switzerland, go to Kerala. You do not say like that, right? You see some preferences of the user. Like for example, you want to basically understand what are the preferences, what is the budget of the customer, so that you can suggest the appropriate, what I can say, appropriate destination points, right?
Yes.
Like for example, if the user prefers, let us say, if the user, so first you are considering the preferences, okay? So let's do it like this. Backwaters, snow, rainfall, something like that, okay? Backwaters, snow, rainfall, places, and so on, okay? You can have multiple, just as an example, okay? So you can have multiple places, but now he gives some of the options. Now, for example, let's say the user selects snow, a snow place where he wants to go to a snow place, okay? Then obviously your next question will be, okay, to a snow place, that is cool, but then what is the budget, right? Is it like below 5 lakhs, or let us say, is it above 5 lakhs? Imagine, okay? Then let's say he say, then based upon his answer, if it is like below 5 lakhs, okay, let's say you say Jammu. If it is above 5 lakhs, let's say you say Switzerland. Okay, just as an example. Now, so based upon the user preferences and based upon the user budget, you are actually suggesting some places, right? Do you think it happens this way? There can be many other questions as well.
Yeah.
But just as a simple example, if you say rainfall, again, then like, you know, how long is your, what is your budget? Then how long are you going to stay? A lot of questions that might come up. Based upon that, you can have multiple questions for all of these, right?
Yeah.
So this is basically a decision tree. That's all. To simply tell, this is a decision tree. So you first ask a question or some preference or something. Okay. Then all the rest of the values are invalid, right? For example, the user says snow. Then you don't consider the places for backwater or rainfall. Then you dig down deeper into snow. So, okay, the preference is snow. Then what? Budget, right? So, for example, if it is budget is less than 5 lakhs, for example, imagine the budget is greater than 5 lakhs, for example, okay? Directly, you may not say Switzerland, right? Again, you might have further preferences again. That if the budget is less than 5 lakhs, then you know, there is no other choice. You go to Jammu. But if the budget is greater than 5 lakhs, you might ask further questions like, you know, how long is the stay? Okay. Based upon the stay, you might suggest a European country or a US, like, you know, just as an example, or yeah, the user can go to Switzerland, the user can go to Iceland also, some or Antarctica also, who knows? Getting my point?
Yep.
So based upon the like maybe then the duration of stay or something else, something any other places also. So do you want to visit any additional places? Something else. He says no, only snow. Wherever I want to see, I should see snow. Something like that. Okay. Just as an example. So you ask the questions, and based upon the questions that the user answers, okay, based upon that, you are going to give some suggestions. Okay. Okay. So any questions on this so far?
No.
Cool. So now here we go. So since we have these, this is basically a decision tree. In a decision tree, you basically will get all these options. You start with some user preference. Okay. From that preference, you start building the various features. You start asking more and more questions. Based upon that, you start building a tree. Okay.
Yeah.
So like for example, snow, then you ask another question. Based upon that, so finally you will go to some answers or the final solution or the final option. Okay. Let us see in a real example, like on my screen. Okay. So it will be easier for us to really understand how we construct a decision tree. Okay. So in this decision tree, you can see that we have 4 features, which is outlook, temperature, humidity, and wind. These are our 4 features. And my final output is decision to play.
Okay.
Okay. So now in outlook, temperature, humidity, and wind, these are the 4 features. So out of all these features, what is the most important feature for me to help to find a decision to play? See, again, for every person, it can vary, right? You might think,
yeah, that's what.
For me,
very
outlook
subjective.
is important. It's subjective. So let us take a mathematical approach to this. Okay. We are going to find something called as a Gini index. Okay. We're going to find something called a Gini index. The lesser the Gini index, the better it is. Okay. The more the important the feature is. Okay. If the Gini index is very less, like 0, it means the feature is very, very important. When I say feature, it is outlook, temperature, humidity, and wind. They are the features. Okay. Is that clear?
Yeah.
Yeah. So let's see the features and their Gini index. So we need to calculate the Gini index of outlook, temperature, humidity, and wind. All these 4.
Okay.
Let us start creating them. So first I take this. So I'm going to take all the unique values of outlook. Okay. So I'm going to say data, remove duplicates. Only. Okay. So these are all the unique values in our outlook column, right?
Yeah.
And then I am going to take my final output cells. Okay. There are oops, sorry. These are the 2 unique values of my output. The output need not be only amongst 2. It can be even more than 2. Okay. Like there can be multiple values as well for our end user, but in this case, we'll start with 2 so that it is easy to understand. Okay.
Okay.
So here you go. Sorry. Done. So now I am going to ask you one question. Okay. In the total outlook, how many times, whenever outlook is sunny, how many times the decision to play is yes? So we'll do an Excel formula. Count if outlook is sunny and the decision to play is yes. Make sense? Count ifs, sorry. It's count ifs. Okay. So in the entire data, is it so? Count ifs entire A is H2 and decision to play is I1. Okay. Okay. I think it is like no.
Is right.
Sunny.
It's 2 only.
It's only 2 whenever outlook is.
Yeah.
Decision to play is yes 2 times, no is 3 times. Okay. Okay. Cool. Okay. So here you go. Right. So I'm going to apply my formula across. So the column A and it is H2, then it should be again, it should be passed on to I2 and J2. So yes. And then again it is E2. And then it is I1, J1. So with this, I am applying this formula across. No, somewhere it's. Sorry, here you go. Okay. So this is the data sector. Okay, cool. We have it. So whenever outlook is like sunny, decision to play is 2 times, no is 3 times. I think like, yes, we already saw that. Right. So whenever outlook is sunny, the decision to play no is 3 times and yes is 2 times, right? Similarly, whenever the outlook is overcast, the decision to play is yes is 4 times, right? And that's what we got. Whenever outlook is overcast, the decision to play is 4 times, right? And so on. So this is our data. Cool. We have it. Now, so the next question, okay? Listen to the question carefully and give an answer, okay? Whenever the outlook is sunny, how many times did we even take a decision? It can be yes or no. How many times did we take a decision to play or not play whenever outlook is sunny? I'm not asking how many times did we play. I'm asking how many times did we take a decision?
5 times.
5 times. And how did we get 5 times?
3 times you decided let's not play, and 2 times it's yes.
Very good. So whenever the outlook is sunny, we considered a play 5 times. Out of that, we played 2 times. We didn't play 3 times, right?
Yeah.
So on. Similarly for overcast and rainfall. So now tell me, whenever outlook is sunny, okay, what is the probability of playing?
2 by 5.
Very good. Right? Agreed?
Yeah.
And whenever outlook is, I hate it when, like, you know, this font keeps on changing. And whenever outlook is no, what is the decision not to play?
3 by 5.
Very good. Okay, here you go. So far, any questions?
No.
Pretty clear?
Yep.
I am now going to ask, I'm going to just do something, just bear with me for a minute, okay? I'm going to now calculate the sum of the squared probability, okay? Let us see why we are doing that, okay? Very shortly. Squared probability means I'm just squaring this number, that's all. Clear? I'm just squaring this number and I'm then calculating the sum of squared probability. Sum of squared probability, yes square plus no square. Okay. Sum of the squared probability is this. Sum of these two. Agreed?
Yep.
What does the sum of the squared probability tell me? Sorry. What does the sum of squared probability tell me?
You're just making sure that it's not minus, so that's why we square it off.
No. Probability will never be minus anyways, because the least value probability can get is 0.
Okay.
So the sum of the squared probability tells us the probability to come to some conclusion. It can be yes or it can be no. It doesn't matter to us. Okay.
Okay.
What is the probability for us to come to some conclusion, either yes or no? For example, the probability of coming to a conclusion is 100%, because whenever outlook is sunny, 100 times, I mean, all the times we have yes, right? So every time we are coming to a perfect conclusion, it can be yes or no, it doesn't matter. For example, I'm marking, for example, let us say, whenever outlook is overcast, okay, in the data, I'm going ahead and you see, I'm changing it to no, okay? Okay. Now you see, whenever outlook is overcast, the decision to play is no, right? So no is 4 times, but still the sum of squared probability didn't change, right? It is still 1. It is actually telling us what is the confidence which we can say that whenever the outlook is some value overcast, okay? With what confidence can we tell that there is a decision to play? It can be yes or it can be no. It doesn't matter to us.
Okay.
Okay. So for example, here either it is yes or it is no. You see, it is 1. What if, like, 2 times we played and 2 times we didn't play? Whenever outlook is overcast, okay? Let us assume. Then what is the confidence with which we can come to some conclusion? For example, okay? It's like a 50%, because out of all the 4 times, 2 times we played, 2 times we didn't play, right? So the confidence to come to some conclusion is only 50%. Agreed?
Yeah.
That's what you got here. It is the confidence, the sum of the squared probabilities will tell us the probability or the confidence with which we can tell that provided the event is outlook being overcast, okay, will give us some conclusion, either it is yes or no. Is this clear?
Yeah. Why are we squaring and why can't we just take the sum of probability?
Sum of probabilities will always give you 1. That's all. 0.6 plus 0.4, it is 1. 0.6 plus 0.4, 1. 0.5 plus 0.51. Sum of probabilities is always equal to 1. Okay. That is the reason why sum of probabilities doesn't work. That is the reason why you square the probabilities and sum them. Okay. That is when it will take you to some particular confidence to tell how much, with what confidence you can tell that a particular event finally gives a given outcome. Okay. Any outcome, it can be A or I mean, amongst the given outcomes. So let me now make it as overcast again and make the values known. Okay. So this is our original data set. No, our original data set is yes. It doesn't matter though. Okay. Yes or no doesn't matter. That's okay. So here you go. So this is our sum of squared probabilities. It tells us the confidence with which we can achieve a final output, right? Gini index is 1 minus the sum of squared probabilities. Okay.
Okay.
So it is like a negative metric, right? So the lesser the Gini index, the higher the confidence we will go towards a final solution. Agreed? Agreed or not? Any questions?
No.
Right? The lesser, because Gini index is a negative indicator, you can tell that, like, I mean, with which confidence you can achieve, you can go to a perfect solution is given by the sum of the squared probabilities. It is 1 minus the sum of squared probabilities. So the lesser the Gini index, the higher the probability that we arrive at a conclusion, some conclusion. Yes or no?
Yeah.
Okay. So now this is the Gini index of every individual feature, right? The overall Gini index of outlook. Okay. can be calculated by the formula the total instances of Sunny into the Gini index of Sunny, okay, plus the total instances of Overcast into the Gini index of Overcast,
Okay.
plus the total instances of rainfall
plus Gini
into the
index of
Gini index
rainfall
of rainfall divided by sum of the total instances, okay, like an average. So what is the Gini index of Outlook?
3.43.
0.34, okay. So this is the Gini index of Outlook. But then we need to calculate the Gini index of temperature, humidity, and wind. Okay.
Got it.
Now let us try to find the Gini index of temperature now. So here you go. I'm going to call this Gini index of temperature. So this is going to be, instead of Outlook, this is going to be temperature. Clear? And now the three values are hot, mild, and cool. These are the three unique values.
Yeah.
So now let us copy this formula here, but let us change. It is not A, but we are referring column B.
B.
Right? Right? And it is not H2, it is H8.
H8.
Right? I again is same. I1, I2 is still okay because it is yes and no. That's all, right? So still this is okay. H8. 1 second. Column B, it is H8, which is hot, okay. And column E, it is I1, okay. It should come up. Why? Weird, okay. Okay. This is our data set again. Whenever temperature is hot, this is it, blah, 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 and so on. Now, the rest of the stuff. Okay. So I'm going to add them. And now I'm going to come up to this probability. Okay. And here it is like this by this. Okay. Some of the squared probabilities. First, we have to calculate the squared probabilities. Then I'm going to calculate the sum of the squared probabilities. Right? And then the Gini index, it is 1 minus the sum of the squared probabilities. And finally, once you calculate this, we are going to calculate the Gini index of temperature. Gini index of temperature is the sum into the Gini index of this plus the sum into the Gini index of this plus sum into Gini index of this divided by sum of all this. Right? So Gini index of temperature is 0.357. Okay. So which one has a lower Gini index? Outlook or temperature?
Outlook.
So still Outlook is only more important feature to calculate temperature, because overall Outlook has a 30, Gini index, you can calculate this as a 1 minus 0.34, which is like 65% confidence. So with Outlook, with the feature called Outlook, you can tell with 65% confidence on what will be the final output.
Okay.
You can use that feature to arrive at a conclusion. Whether it can be yes or no is a different stuff. Okay. Like that.
Okay.
Then let us calculate it for humidity as well. So for humidity, it is Gini index of H. Okay. Humidity, there are two values, high and normal. Okay. Now let us calculate the formula once again. That is, it is now H14 and it is not B anymore, it is C. Okay. So this is the formula. Okay, so the sum of the squared probabilities, it is this by this. The sum of, oh sorry, the sum of the squared
Probability.
probabilities is sum, right?
Yeah.
Sum of these two. And then it is equal to this divided by this.
Yes.
Again, it is equal to no divided by sum. Probabilities. And then the sum of the squared probabilities is equal to this into this, right? And the sum of this, sum of these two, yes and no. Now the Gini index is equal to 1 minus this. And now finally the Gini index of humidity is going to be sum into the Gini index plus sum
into
into
the chain index
x
divided by total of sum.
of sums. 0.367. Okay. So which one has a least Gini index so far?
Outlook.
Still it is outlook. Outlook is still the important factor because we know Gini index is a, I don't say negative indicator, but the lower the Gini, the higher the confidence that we can arrive at a solution, right? Let us do that finally for wind also. Okay. So why not, why to leave that guy separately? So Gini index of wind, that is going to be Gini index of W. So wind, we have two values, weak and strong, right? So how many times? Let us copy the formula. And don't worry if you are like not aware of the formula and all, that is still okay. Because as you might have understood by now that, you know, these formulas and all are not pretty that important, right?
Yeah.
Because anyways, you will do it in you'll do it in Python. This is all something I do so that you can understand better. That's why I do that. This is only for the educational purpose. So here you go. And the probability of yes is 4 divided by 8. Probability of no is also equal to 4 divided by 8. Right? So we have the probability of playing whenever it is weak, whenever it is strong, and then the squared probability whenever it is here, and the sum of the squared probabilities. The Gini index. Okay, and finally the Gini index of wind is sum into its Gini index plus sum into Gini index divided by sum.
Total sum.
Gini index of wind is 0.45. Okay. So which one has the least Gini index?
Outlook.
Outlook. Okay. So outlook is our guy. Okay. So now we are going to create a decision tree in this fashion. Okay. So the one with the least Gini index will always be the first. Okay. So I am going to call outlook here. Okay. Let us create a box for it. Okay. Now, what are the three values of outlook? Sunny, and then overcast and rainfall. So this is sunny, this is overcast, and we have rainfall as well. So I'm going to create 3 data. Okay. So whenever outlook is sunny, overcast, right, and we have 3 options, right?
Yep.
Sunny, overcast, and rainfall. So whenever outlook is sunny, okay, so I am going to limit my data set to only when outlook is sunny. Okay, like this. So this is my updated data set, right?
Yep.
Now, whenever outlook is sunny, what is the next important feature for me? In this data set, I have to repeat this process of calculating the Gini indexes.
Okay.
Clear?
Mm.
Because for in this data set, it is important for me. So because you can see that whenever outlook is sunny, I am going to calculate the Gini index of temperature, temperature of humidity, and Gini index of wind. Okay.
Mm.
So just as an example, let us take this very quickly.
Mm. So again, in this, whatever is the least, the precedent will be that one, the
Exactly.
successor.
Exactly. So in this, let us say that, temperature comes up as the winner, for example. Okay. Or in this case, actually to say, um, I think the most important is humidity, I believe. Because whenever the humidity is high, the decision to play is no. Whenever the humidity is normal, decision to play is yes. You see?
Okay.
It's like a perfect split, right?
Hmm.
So the Gini index will be 0.
Hmm.
Okay. So now it will be like, the tree will be like humidity is the next thing. So whenever outlook is sunny, the next thing that you should see is humidity. Okay.
Hmm.
And if the humidity, like for example, if humidity is like high, what happens? If humidity is high, the decision to play is no, right?
Hmm.
Then the decision to play, if this is high, the decision to play is no. If it is high. Okay.
Okay.
If humidity is less, then the decision to play is yes. Okay.
Hmm.
Whenever outlook is rainfall overcast, the decision to play is always no, I think here, right? Data, whenever outlook is to overcast, decision to play is no, right?
Hmm.
So for that, there is no Gini index, because that's like already very clear forward, right?
Ah.
So here you go. So in this case, whenever outlook is overcast, decision to play is no. Then whenever outlook is rainfall, okay? Whenever outlook is rainfall, okay, then we'll once again see the Gini index, okay? You can see whenever outlook is rainfall, whenever wind is weak, the decision to play is yes. Right? Whenever wind is strong, the decision to play is no. Do you see that?
Yeah.
So again, but because if you take humidity, for example, once humidity is high, decision to play is yes. Humidity is high, once the decision to play is no. We cannot come to a perfect conclusion, right?
Yep.
If we take temperature, for example, when temperature is cool, once the decision to play is yes. When temperature is cool, the decision to play is no once. But whenever wind is weak, in all the instances, whenever wind is weak, like this, the second instance or the fourth instance, it is always yes. Whenever wind is strong, the decision to play is no. You see?
Yeah.
So if you calculate the Gini index for wind, it will be the least Gini index. Okay. So the decision to play will be check out the wind. Wind will come here. Okay. Whenever the wind is weak, okay, the decision to play will be yes.
Yes.
And whenever wind is strong, decision to play will be no. Clear? This is a tree because it starts a tree structure, but unfortunately the root is at the top. Generally for a tree, root will be down, right? It's like an inverted tree.
Okay.
Like imagine just you see it downwards, outlook will be here. Okay. There are 3 branches like this, right? So here humidity will stay. Again, humidity has its own branches. Again, this has its own branches. Wind has its own branches, and so on. Sometimes based upon the data, it can have further splits like this. It can have again 3 branches. It can have again 2 branches. It can keep on splitting, right? Like that. But that's in general, okay? But for this decision tree, you can see how we can see the data. So what we have achieved using this, tomorrow, whenever we have an outlook, okay, whenever we have the decision to play or not, okay, if that is the criteria, then first thing you should look for is outlook.
Okay.
So you ask questions to the users based on their preferences, right? What is your preference? What is your budget? What is your place of like, which kind of like temperature, etc. Similarly, here you are asking, what is the outlook? So tomorrow somebody comes and asks, should I play tomorrow or not? Okay. First you say, okay, what is the outlook tomorrow? Somebody says rainfall. It might rain. Okay. Then what is the approximated wind speed, for example, tomorrow? The winds, they say they will be weak. Then you say, okay, then go ahead and play. That's the outcome. Getting my point?
Yeah.
So based upon this, so you ask certain questions. Based upon those questions, you're going to form a tree. And once you get a tree, then based upon that, you're going to find the solution. Clear?
Yes.
So it's important for you to really understand what is a decision tree, okay, and how a decision tree is created. That is very, very important. Okay. Okay. Okay, so that's it. So that's about a decision tree. But again, as I said, there are a lot of stuff still with a decision tree. For example, in a decision tree, you can keep on increasing the branches whenever the decision is no. In this case, since it's a pretty small example, directly you got conclusions, right?
Yeah.
In real time, you may not. This tree will further split. This tree will further split, and so on until you get a final solution. They keep on splitting, right? So generally what we do is we do not allow our tree to grow till the end. Okay. Getting my point?
Yeah.
Until we reach a conclusion. After 2 or 3 layers, generally we stop it there. Okay. So for example, after this layer, imagine that all the times we are not getting for high, we are getting no. Imagine, okay. Imagine whenever humidity is high, 3 times it is no, and 1 time it is yes. Okay. Imagine. And whenever it is less, 3 times it is yes, 1 time it is no. It's like that, for example.
Okay.
So still we can further split it, right? Because we still didn't get a perfect split. Agreed?
Yeah.
So, but generally we do not do that, okay? Because whenever humidity is high, our probability to play is 3/4, which is 75%, right? Because out of the 4 times, 3 times we didn't play, only 1 time we played. So out of 4 times, the probability to not play is 75%, right?
Yeah.
Similarly, vice versa. Here it is again. I don't say always it should be equal. The probability can be maybe, let's say 60%. That's okay. I'm just giving an example. Okay.
Okay.
So now in this case, there is a high probability for us not playing. And in this play, there is a high probability of playing, right? So we can stop the tree there instead of further splitting it into branches. Okay. We can stop there based upon the probability of one particular output. We can tell that that is the probable outcome.
Okay.
The advantage using this particular technique is if you allow the tree to grow more and more and more and more, okay, it will not generalize to all situations. It will try to point out that specific instance where something happened. Okay. So it may not happen all the times again, right?
Yeah.
On one specific day, it rained and it is sunny also. But that doesn't mean whenever it rains, it will be sunny. Getting my point?
Yeah.
That is the reason why we do not allow the tree to grow completely till the end. That is called a problem of overfitting, okay, which we'll learn a bit later. But that is the reason at times it is a very common practice to stop the tree from completely growing. We allow it to grow till 2 or 3 branches and stop there, and then take the probabilities of each and every class. Okay. And then determine which class is the winner based upon the higher probability.
Okay.
Clear?
Yeah.
And this process of cutting the decision tree instead of growing fully, this is called as pruning. 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 Okay. Pruning is a technique in order to prevent overfitting for you and, to generalize the model better. That's why we do pruning for a decision tree. Okay. Yeah. Any questions on what is a decision tree, etc.?
No.
Clear so far? So decision trees are, again, they are pretty powerful machine learning algorithms. They are like pretty powerful because, and decision trees are comparative to the other algorithms existing. Decision trees are relatively new in the market. Like they are developed maybe some 20 years ago. That's all. They are developed in the Bell laboratories. So they are pretty new. That's a pretty recently developed algorithm, but that's a pretty powerful algorithm. Trust me, that's a very powerful algorithm in determining. Okay. So let us see decision trees in action. Let us once again take our iris data set, because that's a standard data set over which we are doing all our practice, right? So let us so Here you go. I'm not doing all the train test split and all. Maybe I'll split it, but I'm not creating the data frames, all that stuff, because we already know. Okay. So sklearn dot data sets import iris from sklearn dot model selection import test split. Okay. And then from sklearn dot tree import decision classifier. Okay. And again, finally, from learn dot metrics import accuracy score. Okay. So now iris is equal to load iris, and my x is going to be iris dot data, y is equal to dot target, and then xtr xt ytr yt is equal to split my x comma y, the test size 0.1, random state is equal to 0. Done. So tree is equal to decision tree classifier. Okay. Tree dot fit xtr ytr y is equal to tree dot predict t. That's our prediction. So oh, sorry, this is our prediction value. Sorry, my bad. So once we made a prediction, then we are going to compare it with the actual. So my accuracy is equal to accuracy score of YTE and YPRED. So you can YPRED is, oh, it's tree pred, sorry. That's, oops, sorry. What? This is accuracy, and then finally accuracy into so percentage, 100%, right? So for all our given data, the 10 examples or 15 examples, whatever it is, it has made a correct prediction. Clear?
Okay. So what is the prediction here?
If you want to know what are our predictions, they are these. These are my predictions. Okay. So this is the second class, the first class, the zero is iris setosa, right? Versicolor 2 is virginica. Agreed? That's our Y from our target. So you are comparing the decision tree's prediction to our actual values, which is Y test. Okay. Any questions on this?
Can we visualize this in like a tree, like however you did?
We can visualize, but that requires some additional concepts which we'll discuss later. But yes, while visualizing, I'll show you how to visualize a decision tree.
Okay.
But yes, we can do that as well. But when we are speaking about visualizations, let us see visualizing a decision tree too. Okay.
Yeah.
Any questions?
No, I was just trying to understand this result, because this data set, I don't think we have seen it before. So I'm just trying to relate to the example that we worked on Excel, how the result can be visualized. I'm just thinking that, like there, so when it was based on outputs, and we were able to visualize what will be the next this one. So here it's just only numbers. I'm thinking how this can be a decision.
See, it will do like this. For example, it can consider many factors. For example, it can say, for example, let us see. Let's say, for example, let's say I'm going to use a plot tree. Okay. what did we define as a decision tree classifier? Tree. Okay, so let me try to enhance this image if I can get it better. Let me save this image to downloads. Okay, let me open that in downloads. Where did it? Here you go. It's pretty small, okay, but you can actually see like this, okay. If the second value, which is a sepal and sepal width, okay, that's a x of 2 is sepal width, okay. If that is less than 2.45 and so on, then it is making a split,
okay,
you know, and so on. You can see the splits, how it is actually creating a decision tree. So basically here, I mean, this is though it is more optimized form of our like decision trees that I had actually told you, okay. Basically what it does is it tries to start splitting what is the optimum way that I should check so that I can start splitting my tree.
Okay.
For example, you can see if the x of 2, which is the sepal length, is less than 4.95, then if x of 3 is less than 1.65, then so on. You are getting my point? It is actually considering the sepal length, the petal length, the petal width, and so on. Here it is considering, for example, the sepal length, for example. Okay, x of 1. You see that? Okay, and so on. So it actually considers every individual value. What is our sepal length? Based upon that, it further splits. If it is less than this, then go for this, else go for this, and so on. Okay, it creates a tree structure like this. So tomorrow, whenever you have a new data, it actually takes the second argument, okay, which is the petal length. Is it less than 2.45 or not? Okay, and so on. It starts making a split.
Okay.
Clear? So you can use this plot tree, but I mean, but that's, as I said, like I wanted to introduce plottings all separately, but that is how, like, I mean, a decision tree will be plotted.
Okay, what is petal and sepal?
And they are the features, x.
Okay.
Sepal and sepal width, petal and petal width. That is our x, right?
Okay, that in the data set. Oh, cool.
You can see there is dot feature names. The sepal length, the sepal width, petal and petal.
Okay, the data.
This is a two-dimensional array, right? You remember our x? See your x, it contains 4 values, right? Contains 4 values. So every row contains 4 elements. What are the elements? The sepal length is the first one, the sepal width is the second, petal length is the third, and the petal width is the fourth. Okay. For all these 4, there will be a related y. For 5.1 sepal length, 3.5 sepal width, 1.4 petal length, 0.2 petal width, there is a value called 0. 0 means Aristotelian, and so on. Clear?
Yeah.
Any questions on this?
No.
Okay.
These trees are, I think there's something like tree leaves and node, something like that.
Yes. So this is actually the node. Okay. The root node.
Okay.
Every square is our node. Okay. A node. Okay. But so these are the splits are our branches.
Branches.
Again, the branches can have further nodes or leaves again. Getting my point? They are generally called as nodes of it. Okay. Is that clear? Yeah. Any questions as far as decision trees are concerned? No. And again, decision trees are pretty powerful algorithms. Okay. And today, let us once again, on top of decision trees, let us also see one more algorithm called as random forest. Okay. What is random forest does? So what is a forest? A place where there are a lot of trees, lot and lot of trees. Agreed?
Yeah.
So as the name random forest, because it is constructed out of multiple decision trees.
Okay.
You're creating a lot of decision trees, and that is the reason it is a forest. Okay. Why random forest? The reason why it is called a random forest is because you are not considering the entire data set together. Because if you are considering all the data set together to create a tree, you'll always get the same output, right? From our entire data, for example, in our entire data called X, we have 150 records, right? From 150 records, randomly some records, let's say some 100 records, okay, are pulled. And then, of course, there is a special technique in which the data is pulled, but that is a bit out of scope. It goes into pure statistics, okay, which I don't want to go too deep into statistics, okay. But there is a process, it's called like by repetition. Like you pull, for example, out of those 150 examples, you start pulling these randomly, some values again and again, okay. And then you create one data set with 150, but like, you know, I can call 1, I can call 4, I can call 7, I can call 10, again I can call 1, again I can call 3. It's like that, okay. I keep getting my data set and I pull records randomly like that, okay. And then I create for every, so like that I create a first random data set, okay. And for that data set, I will create one decision tree, okay. Again, from the data set, I create again a sample subset of my original data set, okay. Randomly I pull few records and create a subset of the second original data set. Clear? And for that subset data set, I create again a decision tree. Like that, I create multiple decision trees. Here, the data is pulled randomly from the original data set. A subset of the data is pulled, okay. The records are pulled randomly. Then that is the reason why it is called random forest. Once I create, let's say I create 100 decision trees, okay. Now, whenever I get a new record, I pass it through all the 100 decision trees and ask for a solution, okay. Imagine 70 decision trees says that it is a yes, 30 decision trees say it's a no, okay. Which has a majority? Yes has. So I consider yes is the winner. So the outcome is yes. Okay. So in order to use a random forest, you can, it's actually called as an ensembling technique. So it is available under ensemble. Random forest classifier. Okay. You can say random forest classifier is equal to random. Okay. But you can see n estimators is equal to 100. The number of estimators tell the total number of decision trees. You can see here the number of trees in the forest. You can see that. So how many decision trees should be created? Individual decision trees to be created in this random forest. By default, it is 100. Okay. And criteria is Gini. Again, we are using the same Gini index as our criteria. The reason is because each and for every decision tree, again, we use Gini index as our criteria, right?
Okay.
So again, it is not different from a decision tree, but we are creating multiple decision trees together and we are aggregating their results. Make sense? So again, I'm leaving it to the defaults though. So I can say rfc.fit my xtr okay. And I can say rfc underscore prediction is equal to rfc.predict. So this is my predicted value. So I say RFC as accuracy is equal to accuracy score of actuals and RFC underscore predict. This is my accuracy score. Clear? Let me see what is my accuracy score. It's 100% again. Okay.
So what happens when Gini score of, let's say, 2 or 3 features is the same? So how does it consider which one is
not the Gini score? I think you meant the final output. So
the final
100 trees, let us say 50 trees vote for yes and 50 trees vote for no. Is that your question?
Yeah.
So if that is the case, then one of the options will be selected randomly.
Okay.
So for example, it says yes once, okay. For the same criteria, if there is the same voting, then like, you know, the second time it might say no, because randomly one answer will be chosen. Clear?
Okay.
Yeah. This is our random forest classifier.
Okay.
Any questions on this?
No.
You can use, for example, if you can use the random forest and decision tree also for regression, like a nearest neighbor. Okay. For example, if you have a regression problem, you can see as random forest regressor. If you want to use a decision tree for a regression, you can use decision tree regressor. Clear? Now, one quick problem for you. Can you work on this particular problem for Boston dataset? Okay, for a Boston dataset, can you use random forest regressor and tell me what is the mean squared error?
Okay.
Yes.
Now?
Yes.